Controller разлежит the shifted symplectic structures.
So let me give an outline. Of what we'd like to do. So first I want to say something about what is derived algebraic geometry. And this will be a very non-technical introduction. And most of the questions we're going to ask are local, so we're going to focus on what such a thing looks like locally. And second, so there'll be some definitions and some motivation. And then second, we want to talk about special structures. Under moduli spaces. So these special structures will be some generalization of symplectic forms. And for these things to exist and make sense, you really need to work in this context of derived algebraic geometry. So, namely, these will be what people call shifted symplectic structures. And then, using the existence of these shifted symplectic structures, we'll look at local structure of these moduli spaces. So the existence of this special structure will put constraints on what a neighborhood of a point looks like in such a moduli space. So maybe I would say local models of moduli spaces with symplectic structure. And this is a kind of derived theorem. And finally, maybe this will happen after T, I'd like to talk about open questions. So I did some work on this about 2 years ago, and in the last year, I've been working on other things, and I want to return to this, so there are lots of questions. So this is going to be, these local structures are joint work with Vittorio Bussi, Dominic Joyce, and there's a second paper which takes into account some stackiness, and that also has more inventive stuff. Okay. So let me say a bit about what derived algebraic geometry is. So if you're studying varieties or schemes, these are things that locally look like affine varieties or affine schemes. So in classical algebraic geometry for me is going to mean basically schemes. So in classical algebraic geometry, everything is built in terms of commutative rings. And you can define points of your space with values in any commutative ring. And you can do lots of interesting things. You can recover all of true classical algebraic geometry that people did in the 19th century, as well as many generalizations. But you run into some problems. So let's look at the simplest example. If you're looking at things that are somehow finite dimensional, then locally, such a thing, say a scheme of finite type, looks like the zero fiber of some map from one affine space to another. So you have finitely many variables and finitely many relations. So if this function from an to am has components f1 through fm, then the scheme theoretic fiber of this map, so throughout, I should have said this, we're going to fix a field k, and I'm going to assume k has characteristic 0. This will become necessary for the applications, but for now it just makes things simpler. So the scheme fiber is just, its functions are the functions on here modulo those that vanish along the 0 fiber. So polynomials and then variables modulo these n functions. And this fiber can be as singular as you like. So any singularity that appears on a schema of finite type appears on such a thing because they all locally look like this. And one reflection of how singular this thing can be is, well, you can measure the tangent space at a point and see how much bigger it is than expected, given by a dimension of the fiber. But you can look at sort of higher versions of the tangent space as well. So there's something called the tangent complex. So we can consider the tangent complex. Maybe I'm jumping ahead. Let me just say this. This can be as singular as you like. And I'm not going to define the tangent complex yet. I'll do this in a minute. But let me claim that the so-called tangent complex can be of infinite amplitude. So this is some reflection that this scheme can be very, very singular. I'm saying there's an infinite amount of information that you have to take into account if you want to understand the deformation theory of the singularity. And I'll explain what this is a bit later. However, there is something nice that we can always replace this with. There's a kind of derived version of taking the fiber. This is always somehow approximately smooth. And this can be microsized, or sort of virtual complete intersection. So the singularities of this derived fiber are in some sense not too bad. So why could this thing be very singular? If m is small, right? If m is no bigger than n, and I chose these functions at random, nothing bad should happen. The hypersurface defined by f1 should be transverse to that defined by f2, which should be transverse to that defined by f3, and so on. When you intersect them all, everything should be smooth and of the expected dimension. Or at worst, you might get some kind of singularities coming from a complete intersection. So this is if m is less than or equal to n, and these are chosen generically, the intersection, this will have the expected dimension. n minus n, So what can go wrong is if the F1 through Fm are not generic, or if there are too many equations, so there's somehow you get a negative expected dimension. Okay? And how do you test if F1 through Fm are generic? So there's something called the Kazoo complex. There's Kazoo. It's actually not just a complex, but it's a commutative differential graded algebra. And its cohomology measures failure of F1 through Fm to be generic. So what is this thing? It has, we call it KF. So it's going to be a graded commutative algebra. So it's going to be free on generators x1 through xn of degree 0. And it's also going to have generators y1 through ym of degree -1. And it's free on these as a, if you like, supercommutative algebra. So that means you form polynomials in the xi's and in the yi's, except you have a sign rule. So the xi's commute with each other like usual, but these have degree -1, so they anticommute with each other, and they commute with these. Because these anticommute with each other, they behave like a wedge product. So you can take at most m of them together before you get something that's 0. So if you start writing out polynomials in these things, the y's appear with degree at most m. And it has a differential, the Kazoo differential. So this complex, this graded commutative algebra, is free on these things. I just have to tell you what the differential does on the generators, and then I'll extend by the Leibniz rule to a polynomial in these generators. So the differential is going to send things of degree 0 to 0, because there's nothing in degree 1 for it to map to. And it's going to send the generators of degree -1 to these defining functions, f(i). And you extend by the Leibniz rule. So if I have polynomial in these things, let's call it A, another one, say alpha and beta, then I can compute the differential on their product by this graded Leibniz rule. So when I move the differential, which has degree 1, past this thing of degree alpha, I pick up a sign. But otherwise, it's just the Leibniz rule from calculus. And since I defined it on generators, since everything is a polynomial in generators, this defines the differential everywhere. And if you work this out in coordinates, you'll get the same formula that you see on commutative algebra book for the Kazoo complex. But I think this is an easier way to remember what the differential is. Okay. So the first thing to note is, what is the cohomology of this complex in degree 0? Well, everything in degree 0 is killed by the differential. So that's the kernel. Modulo the image of the differential, which is the stuff coming in from degree -1. So cohomology of the Kazoo complex in degree 0 is just polynomials modulo the functions that define our zero fiber. And if the F1 through Fm are generic, so this is a theorem in a commutative algebra book, if F1 through Fm form a so-called regular sequence, which basically means that the hypersurface defined by F2 intersects the one defined by F1 transversely, the one by F3 intersects the intersection of F1 and F2 transversely, and so on. So that in the end you get something of the expected dimension. So if these form a regular sequence, then all other cohomology of this complex is 0. And in this case, working with this Cazul CDGA or with the algebra functions on the zero fiber are equivalent in terms of homotopy. So we have a map here to the functions on the zero fiber, and this here is the quasi-isomorphism. So if you like, this gives a kind of free model, a free differential graded model of this algebra, which might be slightly singular. But in general, you can have this cohomology being non-zero in some negative degree. So it's possible to have some non-zero cohomology for some I strictly less than 0, but it couldn't be any less than minus m because the complex only goes down to degree minus m. Right, so I can only have at most degree m of these things in my polynomials. Okay. And what the idea of derived algebraic geometry is that this cohomology negative degrees for the Cazul complex is actually very important and interesting. This is a feature, not a bug. So in a commutative algebra book, this is considered the good case, and anything that's not a regular sequence you try to ignore. And here, what I want to say is when this is non-zero, when you don't have a regular sequence, what this is telling you is that the Cazul complex is a better thing to work with as functions on your fiber than just the usual functions. So why? Okay. So let me give a definition. It's kind of a heuristic definition. The derived fiber of our map is, so I'm putting this in quotation marks. You have to make sense of what this means. It's not spec of the polynomials modulo the functions. It's spec of this commutative differential graded algebra that agrees in degree 0 in its cohomology with functions of the classical fiber, but it contains some higher information about the way in which these functions are not generic. Okay. And this thing is better behaved than the usual fiber. So this thing is somehow always approximately smooth and always looks like a complete intersection, more or less by the way you've constructed it. is defined by n functions. And the way you see this thing is better behaved is by looking at its tangent and cotangent complex. So I want to say something about that. And if you get nothing else out of this talk, it should be that actually the tangent complex can be a fairly concrete thing. It's not something scary that should be avoided. So I want to talk about the tangent or cotangent complex. So this is due to Quillen and Ulysse. In the context of Quillen, topologists call the cohomology of, I forget if it's tangent or cotangent, they call it Andre Quillen cohomology, or homology. So in homotopical context, that's what it's called, and algebraic geometers call it tangent or cotangent complex. So what is this? The idea is that the cotangent complex, well, it's cohomology. The cotangent complex, say, of an algebra or of a scheme. This is the sort of higher derived functors of the Kähler differentials. And the motivation for this is the following. So how do you end up with higher derived functors? It's because you have some kind of sequence which is exact on one side but not on the other, and you want to complete it to some long exact sequence. So given a morphism of schemes, you can take them to the affine if you like. We have a right exact sequence. So I can pull back the Kähler differentials on x. I'm going to pull back on one form, so I get a map of Kähler differentials on y. And this has a cokernel, which is the relative Kähler differentials, x over a. Sorry, you're right. Thank you. The pull back on y. And if the map x is a submersion, so x and y are smooth and the tangent map is projected everywhere, then you know that this thing will be locally free. You know its rank is rank of this minus rank of that. And this whole thing will be exact. In general, this doesn't happen because the tangent map may be singular somewhere. So this is only a right exact sequence, and you'd like to know what fits in here. And the answer to this is cohomology of the cotangent complex. So, claim that there exists a theory of the cotangent complex, and I'm going to tell you very concretely what it looks like on affines. So how to compute it on an affine. So there exists a theory of cotangent complex For some reason, I don't really understand. It's called L. I think L is left, but maybe there's a better reason. Because somehow it's going to appear on the left.
The name of the scene is Luke.
What's that?
The name of the scene is Luke.
Luke? Yes, but I think John Quillen also called it L. Quillen was perhaps more modest.
Also, ice in the sun.
Okay, so anyways, there exists a theory of cotangent complex with the following nice properties. So first is it's a complex with quasi-coherent cohomology, and its zeroth cohomology is just the Kähler differentials. And it completes that long exact sequence. So there is, if you like derived categories, you would say there is an exact triangle. Like this, whose associated long exact sequence of cohomology completes this thing. So this is kind of like an exact sequence of complexes. If you take cohomology, you get a long exact sequence. Complete star, where star is this thing. So those are the desiderata, the things that you want of a theory of the cotangent complex, and then you have to do lots of work to actually construct this theory, and you wrote a big book about this. Nowadays, I think it's a lot easier than it used to be because we have better technology. It's still some work. Okay, so what does this look like on affines? When you talk about Kähler differentials, on an affine, you do this very concretely, right? It satisfies some universal property, and you just construct the thing that satisfies that universal property. So here, it's going to be the same thing. It's going to be a kind of Kähler differential construction, but in a differential graded setting. So on affines, the theory looks like the following. In order to compute derived functors, you're going to have to resolve something. But this is going to be a non-abelian resolution. It's going to be a resolution of algebra functions on x or on y. So given, say, a commutative algebra, maybe over your ground field, you can do this in a very general setting and over things in positive or mixed characteristic, but you have to use more simplicial technology. So I'm going to stick to something over our ground field of characteristic 0. It'll be much more concrete. So given a commutative algebra over our ground field, call it A, we need to resolve it. By algebras which are somehow smooth in various degrees. So this is going to be by a commutative differential graded algebra, something like a Drizzle complex. I'm going to call it A tilde. Which, so my convention is that my commutative differential graded algebras are cohomologically graded and bounded above at 0. And the kind of, when you resolve something, you resolve it by something nice. So in homological algebra, you resolve modules by free modules or projected modules. here we're resolving an algebra. What counts as a nice algebra is that you ask that the stuff in degree 0 be a smooth algebra, and you ask that the stuff in higher degrees be free over that. So it's like the Kazoo complex. In degree 0 have polynomials. Certainly affine space is smooth. And then I had some other generators which were free over that. So A0 is smooth. You could even take it to be free if you want. But this gives us more flexibility. And the whole thing is free over the degree 0 part. There might be infinitely many degrees in which you need generators, but it should be free. And the resolution means that I have a map here, which is a quasi-isomorphism. And if A is already smooth, you could just take this to be the thing itself. If A was functions on some complete intersection, you could just take the Kazoo complex, because we saw the Kazoo complex had no cohomology in higher degrees. It was actually a resolution of the algebra. But if it's worse than a complete intersection, then this resolution will go on forever. You will need infinitely many generators to do this resolution. So if A is smooth, you don't need to do anything. It's already resolved. If A is a complete intersection, or local complete intersection, then a Kazoo type complex will work. But if A is worse, it's a fact. It's a fact that there's no finitely generated resolution. Any resolution has generators in infinitely many degrees. And this is the reason that things that are worse than LCI are really bad. Okay? That if you try to resolve them in this non-abelian context, they have infinite amplitude. And this is the reason that this Kazoo complex, even when it's not acyclic in higher degrees, is a really nice thing because it's bounded. It's generated in degree 0 and -1. So in terms of these resolutions, what is the cotangent complex? So the cotangent complex is represented, it's defined as a quasi-isomorphism. This is nothing but the Kähler differentials for a resolution. And the Kähler differentials for a commutative differential graded algebra are defined basically the same way as the usual Kähler differentials. So what do the Kähler differentials do? They co-represent derivations. Now you just ask, if you have a commutative differential graded algebra, you look at differential graded modules over it, and you look for derivations into those. And you ask that that be co-represented by something. And the same construction works. You take derived differentials of elements of your algebra modulo the derivation relation. So that's it. So This cotangent complex, if you have a concrete resolution, is something very concrete. It's just scalar differentials. Let's do an example. So let's do the Kazulf complex type example. Let's say the algebra we resolved by was a Kazulf complex, and our algebra was already a local complete intersection. Then the Kähler differentials on this thing, they look a lot like Kähler differentials for a polynomial algebra. So they're generated by derived differentials of the generators. Okay. And the additional feature that we have here is that this is no longer just a module, but a differential graded module, because the algebra has a differential on it that induces a differential on the Kähler differentials. So with differential, D applied to this generator, so that's just 0, because D sends xi to 0. And D of the other generator, I just replace yi with fi, which is what D sends yi to. So I get the derived differential of fi. And that's something very explicit that you can compute. Okay. So if you have a Kazul complex, you can compute the cohomology of this cotangent complex.
Shouldn't there be a minus sign?
In front of this one.
Yeah.
It depends on the convention. So it depends whether you think of, I think, the derived differential as having degree 0 or degree -1. Yeah. And there are different conventions possible in the literature, and so that's the kind of fundamental choice you make, and then you have to make everything else consistent with that. So my convention is the derived differential has degree 0 as a derivation. Okay, so anyway, the point of this, the conclusion, is that the cotangent complex of the derived fiber, represented by spec of the Kazul complex, is always something manageable. This is always manageable. But if the classical fiber, just the usual scheme theoretic fiber, is worse than LCI, then to compute its cotangent complex, you'll have to take an infinitely large resolution. You'll be doing something like this, except you're going to have generating variables at infinitely many degrees, and it's horrible. You don't want to go there. So for very singular classical schemes, it's horrible. I would say impossible. Maybe there's some particular example in which you can compute something, but in general, it's just impossible. So this is some very basic introduction to the local or affine theory. The idea is that instead of working with schemes covered by affines which are very singular, and for which you have no control over the deformation theory. Instead, you work with some kind of generalized differential graded schemes which are covered by nice commutative differential graded algebras. And then we're going to apply this to some interesting examples of moduli spaces. So in derived algebraic geometry, you cover a derived scheme or derived stack with things of the form spec A tilde, where A tilde is some nice. I mean, you can define the theory for non-nice things as well, but in practice, you study those things which are covered by this, where A tilde is some nice differential graded algebra. It might be a Kazoo complex, or it might be something somewhat bigger, but still finitely generated. So maybe you also have some generators in degree -2 and in degree -3, but eventually it's finitely generated. I mean, I'll be more concrete in a minute. So we're going to look at some moduli spaces. So if I give you not just, if I give you a scheme that appears in nature as a solution to some problem you want to solve, and then I ask you, okay, here's a singular point on it. Tell me what's the cohomology of the tangent complex in degree 2, or 1 even. In general, there's no one knows how to do that. So there's no way to answer this question. But the point is going to be on the derived version of the moduli space. You usually know what the answer to that question is, and it's useful to know the answer. Pardon? Yeah. So you have to choose a resolution, but this resolution will be infinitely long. And there are lots of choices involved, and the differential can be very complicated. And if I give you even something more classical and more finite, if I give you a randomly chosen vector bundle on some variety and ask you to control the sheaf cohomology. So this is the idea of derived algebraic geometry. The upshot of this is going to be, we're going to have nice cotangent complexes with nice differential forms on these moduli spaces, which are not really possible in classical settings. So now I want to look at some examples from moduli spaces. But before that, are there any questions about these vague genealogies? Alexei already asked some question. Maybe the other Alexei. Okay. So this is just one motivation, thinking about zero fibers. Here's another motivation where we're actually going to be able to say something very interesting. So at the very end, the conclusion will be some theorem which can be formulated completely in classical algebraic geometry, but the proof requires this derived structure. So now we're going to look at, let's apply this to moduli spaces. Apply this to moduli spaces of, let's say, vector bundles, coherent sheaves, more generally perfect complexes or objects in the bounded derived category. On some variety X. Okay. And I want to look at 3 examples of increasing complexity. So X is a curve, X is a surface, X is a threefold. And so if x a curve. So here, let's say variety x, let's say smooth and projective. So it's not going to be the underlying variety that is singular, it's going to be some moduli space associated to it. So if x is a curve of genus G, maybe the genus doesn't matter for what I want to say, consider a moduli space M of, say, stable vector bundles. All I really care about is that they're simple, so their endomorphisms are just scalars. Moduli space M of stable vector bundles on X. Okay. Then, if I pick one, I know what the tangent space to M is at a given vector bundle. Let me say, sorry, vector bundles on X of fixed Chern character. Right, so I have a bunch of connected components of the moduli space. I pick one connected component where I fix the topological type of the vector bundle. Okay. Then we do know how to compute the tangent space at a point. Always, this is the space of extensions from E to E. So these are first-order deformations of the vector bundle. I'm letting it be a vector bundle for simplicity. If you want to do something more general, you probably already know what might have to change. So here's the tangent space. We'd like to compute its dimension. And so Riemann-Roch tells us something. Riemann-Roch tells us how to compute the Euler characteristic of vector bundles in terms of their Chern characters. Is that unrelated? Okay, so I can compute the Euler characteristic of an endomorphism bundle. Right, so since this is a vector bundle, this is H1 of the endomorphism bundle. Okay, if it's not a vector bundle, then you have to be clever and derived, and then I'll let you do it. So this is the Chern character of the endomorphism bundle times the Todd class of X integrated over your curve. And the point is that this quantity here depends only on the Chern character of E. So it doesn't depend on the particular point. It's constant across the moduli space. So this is dimension of H naught, then endomorphism bundle, minus dimension of H1 of the endomorphism. And since I assumed that we were in the setting of stable vector bundles, this is always one-dimensional. They're only scalar endomorphisms of the bundle. Okay, and so we can actually compute this then in terms of the Chern characters. So the conclusion is that this dimension of this tangent space is constant on M. Okay? And so M is smooth. I mean, you need to know a little more about M, but it's smooth. So that's example 1. So that's the easy case. Example 2 is x is a surface. M as before. So a moduli space of stable bundles on the surface. Fixed Charon character. We also have Riemann-Roch, but it's not as useful. So the Euler characteristic of the endomorphism level at a point. Again, always, the tangent space is something which abstractly we know what it is, and we want to compute its dimension. So Riemann-Roch says, well, maybe I don't know the dimension of x1, but I know the alternating sum of dimensions of x groups. So same formula gives you dimension of x0 minus dimension of x1 plus dimension of x2. And if the bundle is stable, you know this is one-dimensional, but you don't really know anything about x2. And in fact, the dimension of x2 can jump around. So, in general, the dimension of x2 and therefore the dimension of x1, which is the dimension of our tangent space, depends not just on the Charon character, but on the actual bundle, the actual point on the moduli space. So it depends on E itself. So the moduli space of stable bundles of fixed Charon character is in general singular. And you can find in Hoybrechts and Lane some results. You say, well, it's generically smooth, and under certain hypotheses, singularities appear in codimension 2 and blah, 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 but in general it's singular. There's one special case in which you can say something. It's the case in which you can relate x2 to x0, which is something you do know. So seriality relates x2 to x0, so this Hom, from E to the twist of E by the canonical bundle. This is seriality. And if the canonical bundle happens to be trivial, then we do know the dimension, because we know the dimension of x0 if E is stable. So if we can trivialize the canonical bundle, so X is a K3 surface for an abelian surface, then we're done. Okay. Then dimension of x2 equals 1, and dimension of x1 is constant. It's given just by Riemann-Roch. Okay, so this is the nice case for surfaces when the canonical bundle is trivialized. Then you can do something. And then the third example
the action works as an action.
Pardon?
And you don't need it to be trivial, right? If it's negative, I mean, it's also then it's action.
Sure. So there's more than one nice case. And then, well, third, let X be a threefold, repeat the story. Riemann-Roch tells you how to compute the Wheeler characteristic again. And now it's telling us less and less as the dimension grows. But still, we can ask, is there something interesting that we can see if the canonical bundle is trivialized? So if the canonical bundle is trivialized, in some sense it tells you nothing. It says that x1 is dual to x2. This appears with a minus, this appears with a plus, they cancel. x0 is dual to x3, they cancel. So if the canonical bundle is trivialized, so say for Claudiel threefold, then this is always 0. And so you might think it's telling you nothing. It certainly doesn't tell you the dimension of x1. And in fact, so it tells you nothing about the dimension of x1. And in fact, the dimension of x1 can be all over the place. So you get nothing. About the dimension of x1. And M is known to be very singular in general. So in the case of surfaces, I said there were some results where you could control the codimension in which singularities appeared. There were some nice cases and so on. For threefolds, there's essentially no nice cases that you can think of. So even for Hilbert schema points on a threefold, I think this is already singular, I think already for 3 points, definitely for 4. Where for surfaces, the Hilbert schema points is always. So it seems like we're not going to get very far in setting these moduli spaces of bundles on threefolds by the same kinds of arguments that work for curves and surfaces. And on the other hand, maybe this isn't telling us nothing. It suggests that if things were generic, then somehow you expect the moduli space to be at dimension 0. So there's an expectation that M should be of so-called virtual dimension 0. And so you should be able to count the number of points. And this is the subject of Donaldson-Thomas theory. So this virtual number, you have to figure out what this virtual number means. But you can define some virtual number, and this is the so-called BT invariant associated to this choice of chain character. So there is some interesting theory you can do with these moduli spaces, but you have to put this word virtual all over the place. And it turns out that every place virtual appears, there's actually a good explanation for it in terms of derived algebraic geometry. So the point is to take Riemann-Roch very seriously. Riemann-Roch is telling you that, well, maybe you shouldn't care only about x1. Maybe you should care about all of them at once. And maybe you should seek a moduli space whose tangent information involves not only x1, but all of the x groups. So that the solution to these difficulties with these singularities is to consider the derived version of this. I'm just going to write it with a fancy M. So if M were a scheme that had a sheaf of commutative algebras on it, this would be a derived scheme with a sheaf of differential graded commutative algebras on it. And the cohomology in degree 0 would recover this, but it would contain some higher cohomological information. So one nice property would be that this tangent complex, which is dual to this cotangent complex that I defined, it will turn out to be this. So what is this complex on? It's the complex whose cohomology in degree 0 is x0 and degree 1 is x1 and so on. You put down a shift so that the x1 appears in degree 0. So the zeroth cohomology of this is just the tangent space to the classical moduli space. But it knows about Riemann-Roch, and it's a tangent complex which is bounded. So this is telling you that this thing is approximately smooth. If you model it locally by commutative differential graded algebras, everything is finitely generated. And the point is this thing isn't just a dream, it actually exists, and you can prove theorems about it.
When do you think is the right moment?
I think I'll wish to. So let me just assert that this thing exists, and then we'll say more about it. So, it exists. Okay, so we'll say something interesting about it after tea.
Sorry, when do you expect that the term should go virtual dimension 0?
So the definition of this virtual dimension, essentially, is the Euler characteristic of this derived tangent complex. And Riemann-Roch always computes that. So the virtual dimension is just the number given by Riemann-Roch.
Probably it is a Euler characteristic that have three forms from E3, right?
So I was assuming that the bundles were stable for simplicity, and you have to do that in the classical case in order for things not to be too singular. This allows you now to consider the non-stable locus of the moduli space as well.
Yeah, I'm saying even if it's stable, it still has some of it.
That's right. So in the case where it's stable, strictly speaking, the moduli space is some kind of stack, but it's a very simple stack. So the stabilizers are constant. And you can factor them off in a natural way to be left with, I think in general it's an algebraic space, and sometimes it's a scheme. So there's a natural way to get out of it. Yeah, but there's a natural way to do it. There's no choice involved, because if it's stable, then the stabilizer groups are locally constant, and you can factor them off. Yeah, so in that case, no, in that case, it's still, if you factor it off, essentially what you're doing is fixing the determinant of the vector bundle. And then you kill x0 and x3, and you still get something that cancels out. So you'll get the traceless part of this and the traceless part of that, and they'll still cancel. Yeah. Yeah, sorry.
Please go on. So you were going to tell us why it exists?
Why it exists, yes. it's kind of a tautology. So how do you, if you're doing just vector bundles, basically you're looking at maps into VGLN. So you first show VGLN exists as an Artin stack, and then you show there exists a mapping stack from your thing to VGLN. And then you have to prove nice properties about it. So it's mostly tautological. It's not. It's nice that it exists, but this isn't sort of the really difficult thing that one wants to say. I can write down about the mapping stack if you want. So one. So these are kind of tautologies, are part of the general setup. So in the theory of if you were just doing Artin stacks or derived stacks, you would show VGLN exists. So something representing vector bundles exists in derived algebraic geometry or in classical algebraic geometry. And there exists mapping stacks. So there's always a stack of maps between any two stacks, but you have to show that this is, again, algebraic. And there's a kind of, I mean, roughly you construct an atlas in the same way you would normally, just for an Artin stack.
What does algebraic stack?
It means roughly that there's some really huge affine thing, affine derived scheme, which surjects onto it, and then there's some conditions on the fiber products. Usually smooth. I mean, I'm not sure. Smooth in this sense. Yeah. So if you, what is an Artin stack? It's a stack which has a morphism from some affine, which has some representability conditions on the diagonal, which is smooth. Smooth in the sense, roughly, that the relative cotangent complex is locally free. So it's very similar. You just mimic the usual definition of the Artin stack. So the effect of that is you can define everything by pulling back to an atlas. If you just had some general set that was not covered by an affine thing, you wouldn't know how to compute anything on it. So maybe we should.
Скорее всего, делать все наоборот, и запишу все задачи. Им уже приходилось проверять 6 страниц экзамена. Я почему-то на 6 страниц
очень легко дальше, если количество соответствует. Выгнали сахар. Своих учеников.
Ну да, то есть они там сдавали статистику, либо... Там что-то для меня
Сейчас я хочу очень синтетически. Это разве комплекс вашей
Требует семинар ходить или нет? Каждый день. Там было лучше. Доклад должен длиться 15 минут. Доклад, а здесь 16. Нет, я посмотрел программу. То есть, ну, кто анонсировал его после вас? А, нет, после меня, Матвей. Причем он нормально работает. Другое дело, ну, как бы, целый, с какими энтузиастами придется выжить. Вот нам, по-моему, с вами, ну, после Матвеева можно уходить в этот день, да? Ну, прикинул. Ну, то есть, да, но там надо понять, сколько посетить лекции неприлично. Это самое сложное. Но при этом какие-то там все-таки будут мероприятия. Открытие.
Не, ну на открытие
Как раз на них надо.
Нет, на открытие, безусловно, надо сходить, но на закрытие, как у меня, я думаю, получится. Я немножко боюсь опоздать на кухню. Потому что брат там раньше уходит, в 11. Потому что поехать.
Нет, там же из Петербурга. Вас никто не вывезет из Петербурга. Если вы останетесь там, если вы можете туда, надо как-то с этим быть. Вы туда просто не ехать.
Нет, я вот так и про себя решил, что надо дальше. Я лучше в Петербург не так себе. Вместо лекции.
Ну, или там
Вот салют, он часов 10. Салют обычно часов 10 вечера.
не, ну вот как раз может вам не лень туда уехать.
Я теперь дом помогу, салют показывает, что это в нашем переводе, когда было форма, И ситуация получалась, того, что у меня проверено. Вот прям под окном моего дома устроена площадка, с которой бабахают этот самолет. И так здорово,
Официально.
да, совершенно официально. Очень здорово, перед окном.
Я вот под Новый год не задумывался, была официальная. У меня под окном это было официально, но ребят стало много денег.
Нет, ребят стало много денег. Новый год ребят стало своих друзей.
Да, сам вообще.
Нет, я бы такой профессиональный смотреть, потому что очень здоровый у меня. Они заранее притащили много каких-то порядочных устройств. Все выбирать не никого.
Ну тогда